Hello. Well, today I'd like to talk to you a little bit about natural language processing. So let's jump in. So what is natural language processing, or NLP? So it's really the intersection of human language and computation. So it's getting computers to be able to understand and generate human language. And this is a very complex task, but as you'll see, it's actually built up from a large number of smaller constituent parts. So we actually start from very simple rules and build up there, and we can get to very, very complex models of how language works and how things are communicated using language via computers. So one part of NLP is natural language understanding. This is getting computers to understand spoken or written language, the structures within it, the meaning within it. So things like speech recognition, your Alexa or Siri understanding what you're saying, and be able to understand what we're talking about, given elements within a sentence or paragraph. And things like understanding the sentiment. Is someone being positive or negative? Are they being sarcastic or ironic? Which is a very tricky problem. The other part of the NLP area is natural language generation. So this is building on a lot of the work already on understanding, but using that to generate new text responses, sentences, stories. All these different things require an incredible amount of work on the computer to be able to construct a coherent bit of text, a bit of language that we can understand as humans. So how did NLP develop? So it's been going for a while now, and the whole research field started with a rules-based system. So in school, we learned our grammar, and from that, there's set rules of this word must follow this word. These two words must follow this word. If the word is in this context, it means something else. And it's using these rules, you can do some natural language processing. So you can get some idea of what we're talking about, what is the subject of a given bit of text, things like that. But it quickly falls down when it comes to more complex uses of language. And as soon as it's exposed to things that don't strictly follow the rules, which is a lot of language, frankly, then you run into real problems. From this point, we start to think, okay, based on these rules, still using these rules as a fundamental foundation, what else can we do? And we start to look at large amounts of text and do some mathematics on it, so some statistical analysis on what are the chances or the probabilities of, given a certain bit of text here, what are the chances that a different bit of text appears here? And you'll see this crop up later on as well. So using this, we looked at very large amounts of data. A good example would be some of the first language translation. Automatic language translation is a very, very tricky problem. So the first attempts at this were actually based on EU laws, because all the laws that are set out in the EU have to be produced in the member states' languages. So you have basically this like-for-like comparison, this Rosetta Stone. So you can say, okay, given a given concept in German, this is the same concept legally in French. So you actually do some translation. And this worked really well for legal terms, but as soon as it went outside the legal realm, it fell down. This is a common problem where the rules work great as long as the text itself stays within those rules, but frequently language is very fluent and very flexible and is used for lots of different purposes and repurposed. So we have to think of more generalizable, more robust models of how we go about understanding language. And that takes us on to the most recent development in this area, which is use of neural networks. So this is, again, taking a step above just mere statistics of what are the chances of a given word appearing after a previous one. It's using these models to look at massive amounts of data and get an idea of the meaning of the concepts behind words. I'll talk a little bit about that later on in my education piece, about understanding what is meant by a given bit of text. If you show it enough examples of text and context, it can understand what is meant by a given bit of text, and then that is independent of how it might be expressed. So we can actually sort of abstract away some of the meaning there, which is really important, because if we have that meaning, we can express it in a few different ways. We might be able to match it, even if it's not exactly the same text, but the same meaning. So really powerful steps forward. And this is enabled by our use of neural networks or machine learning in natural language processing. So in terms of the understanding side, there's two parts we have to understand. The first is the syntactic side, so the grammar. Have to understand, okay, what are these different parts of a sentence? Where are the verbs, where are the nouns, where are the adjectives, etc. And the next stage is a semantic part. So what is meant by these individual words, by the sentence as a whole? Okay, so 2 parts of this problem. So on the syntactic side, there's a few different tools we have. For any given bit of text, we do a lot of processing first to sort of make it easily digestible by our models. Because our models don't have to read it in the same way we do. So we want to simplify it in some ways. So one of those ways is stemming. So where a given word has lots of different variations, say different tenses, etc., we can actually stem that down to its core word. Okay, so for instance, the word mover, moved, moves, can all be stemmed down to the word move. So the model just needs to know about the concept to move, rather than all those different variations. We can use natural language understanding to find parts of speech. So use these sort of fundamental rules of grammar to say, okay, that's a noun, there's a subject, there's a verb, all these different things. So we can use these basic syntactic rules to help us understand and help the machine understand the basic structures of the text. And things like breaking things into sentences. So this should be fairly trivial. It is for us, but for a computer to do it, there's actually a few little edge cases, as we say. So we would say just, okay, every full stop, break it. Okay, every question mark, break it. But there are occurrences where there's full stops and punctuation where maybe there wouldn't be normally. For instance, sort of e.g. or i.e. or etc. have punctuation in them. So you've got to find these occurrences where that's not actually a break in a sentence. This is just a contraction or a shortening of a given word, for instance. So it's not quite as easy as it seems sometimes, but we can develop these rules that can basically process this text. So break it into sentences, break it into individual parts of speech, and then stem it down to the core word that lets the machine understand more easily what is going on. On the meaning side, it's a little bit more complex. So here we have to try and work out what is being talked about. So again, we can train on large models on previous corpora of text. So it can understand, say, what is meant by, what is a person, what is a time. It can find these elements. And this is a very tricky problem. And again, that'll be talked about in the later talks. But it's one example of using the meaning of the text as a natural language processing task. Relationship extraction is another example of this sort of task. So in a given bit of text, who is talking about who? Is this in the third person, the third person? Things like that we can see instinctually because we're bathed in language all the time. But to get a computer to do it is actually quite a tricky problem. And another example would be argument mining. So for instance, in a given bit of text, a legal example would be a good one. What is the premise of this argument? What is the main argument itself? What are any counter arguments and rebuttals in there in the text? And finding these structures is a very important task because it lets us basically import all of this data that is in the world around us into a mode that the computer can use, but it's very tricky. So on the other side, the natural language generation, a good example would be automatic summarization. So taking longer bits of text and automatically generating a little snippet, maybe for social media or for just an overview of the text, so we don't have to read the whole thing. So what we have to do is create a model of the supplied text, a whole article, say, structurally and semantically. So how is it structured? What are the different sentences? What are the different sentences doing? And also what are the sentences talking about? What are the concepts? Because when you summarize, you want to keep the same concepts, the key concepts there, but avoid any duplication, for instance. So we need to understand what each sentence is talking about as well. Then we need to determine the complexity of each element. So for any given sentence, how complex is it? Can they be combined into a simpler version that is shorter? Remove those most complex elements, those duplicated elements, and generate a coherent response based on what is left. So by the time it gets to this, the model isn't working with the original text, it's working with the stemmed, condensed version. So it has the key concepts, the key words used, and uses that basis then to generate something for us again. So it's an example again of the intermediary representations of language. The machines aren't using the same methods to understand and store and process language that we would. They're taking an intermediary abstraction. Another example for natural language generation would be question answering. So you've got to parse and understand the question. So a question is submitted. So what are they asking? What is it about? How are they asking it? They're really important things to know. And then you've got to generate a coherent response. So based on the data source, whatever it may be your back end about the store you're running or the club you're running, whatever it may be, you've got to generate a sensible, coherent response that answers the question as you understand it. Now, I'd like to finish up with a quick example of using one of these large models and what they can do. So you might have heard of GPT-3. It's a very large machine learning, a deep learning model for manipulating language. And it takes a relatively simple approach fundamentally in that it looked at a lot of text online and tries to predict, given the previous text, and there's quite a lot of context, looked at a few thousand words, given the previous few thousand words, what is the most sensible, most likely, most useful next word or next set of words coming after that. And because it's looked at so much data, it's looked at many hundreds of billions of bits of text across all the web, it's seen examples of everything. So it can, if you give it some text, it can say, okay, what's a good response to that? So it's a new kind of interaction with these models, where before you'd be setting up these like pipelines, basically, okay, what's the question? Can we break it apart? Can we answer it? Whereas now we're much more moving into the realm of, okay, think of a good prompt for this large language model, something that can predict a news. So I'll give you a quick example of that. So here we see a little playground for GPT-3. And you give it a prompt. So you have to give it some text, and it sees that text and it gives what it thinks is a sensible answer to that. So we're asking it a question. We wanted to brainstorm some ideas combining AI and Scotland. Okay, so this hasn't been hard coded in it. It probably hasn't been asked before by anyone. But this massive model with 175 billion parameters, looking at many, many billions of bits of text, has some understanding of the meaning, the semantics behind brainstorming. Means, okay, come up with a few ideas, right? It knows what AI is semantically, it knows what Scotland is. It's seen lots of examples of writing about Scotland and what Scotland involves, and it can give us some answers. So let's submit this. This is live to the API. So here's some examples. So we can see here different ideas of what an AI would do in Scotland. So some of them are relatively generic. Okay, a Scottish AI company that specializes in developing chatbots for customer service purposes. Okay, that could be anywhere. Farmers, it's seen obviously as farming in Scotland is a major industry. Tourism, okay, so it's thinking of, it's not just saying tourism, it's saying a mobile app that uses AI to help tourists explore Scotland and find the best places to visit based on their interests. Okay, there's also an interesting one here, the AI system that assists police in Scotland with solving crimes. Okay, so obviously the crime writing genre is well featured in Scottish literature. So that's got in here. And then, for instance, it's all about context. It's seen millions and millions of bits of text about Scotland. It knows what Scotland is about. It knows what things people might be interested in with Scotland. And this is a good example of this last one, a project that uses AI to map out all the whiskey distilleries in Scotland and create virtual tours of them. So it's not just finding things that relate to Scotland. It's not just thinking of ideas of how to combine AI and those things. It's also imagining to construct coherent sentences that we can understand, that are syntactically and semantically correct. Okay, they might not be good ideas, but they make sense in some sense. And that's an example of the sort of thing that is possible with these systems, all based on those fundamental rules of understanding text, breaking it down. And if you look at large enough amounts of data, you can get incredibly powerful models that let you understand and generate natural language.